Welcome to this explainer, where we're going to break down the actual magic behind the curtain of modern artificial intelligence. Have you ever wondered what's really going on inside these incredibly powerful systems that seem to be taking over the world? Well, today, we're going to look under the hood. But before we dive in, I want you to think about how tools like ChatGPT answer complex medical questions, or how self-driving cars manage to recognize roads, stop signs, and pedestrians. Are they really thinking like we do? Is there a digital brain pondering these problems, or is something entirely different happening behind the scenes? We're going to answer that by walking through the entire pipeline. We'll cover what AI learning actually is, how data fuels the process, converting reality into numbers, the training loop, gradient descent, and finally, testing the model. Let's dive right in. Okay, Section 1, what is AI learning? To really understand machine learning, it actually helps to look at ourselves first. When a human child learns to identify a cat, they do it through the experience of seeing fur, pointy ears, and whiskers over time. At first, they might point at a small dog and call it a cat. We've all seen that, right? But through repeated physical senses and corrections, the brain eventually recognizes the pattern. Well, AI learns in a strikingly similar way. But instead of physical interaction, it learns by analyzing massive amounts of data to find mathematical relationships. Which brings us to Section 2, data, the fuel for AI. Here is the absolute truth. Without data, an AI model is essentially an empty brain with zero life experience. Data is the absolute lifeblood of modern AI. Just look at some everyday examples. A spam filter learns from millions of emails that were explicitly labeled as spam or not spam. Netflix learns from your exact behavior, literally what movies you watch, pause, skip, or like. Self-driving cars? They learn from millions of road images and driving behaviors. And large language models like ChatGPT learn from enormous amounts of text data. We're talking books, websites, articles, and research papers. Whether it's processing your movie preferences or absorbing medical textbooks, data is absolutely the new oil that powers these systems. But here's the catch. Real-world data is incredibly messy and incomplete. It has to go through a strict pipeline from reality to prediction. We always start with data collection from reality, gathering the raw stuff. But then comes data annotation, where we label it so the machine can actually understand what it's looking at. Next is data cleaning. This is where we resize images, correct errors, and remove duplicate records. Only after all of this rigorous pre-processing does the training data actually reach the machine learning model to generate a prediction. The golden rule here? Good data creates good AI, bad data creates bad AI. All right, Section 3, converting reality into numbers. So once we have a pristine, clean data set, we face a major translation issue. Computers do not understand words, pictures, or sounds like we do. They only need numbers. So a word in a prompt is broken down into smaller units called tokens and assigned a numerical token ID. For instance, the word companies becomes the number 2. The word download becomes the number 3. If we're dealing with images, a single photo is broken down into millions of tiny pixels, and each pixel is represented by its red, green, and blue color values, numbers ranging from 0 to 255. This numerical representation is the only language the computer speaks. It allows the AI model to process our entire reality mathematically. Moving on to Section 4, the AI training loop. Now that our reality has been translated into numbers, it can finally be fed into an AI model, like a neural network. Think of this as the brain searching for mathematical relationships. Training is really just a continuous, incredibly fast loop. First, the model receives the input data, say the pixels of a cat image. Second, it makes a prediction. Early on, it might guess dog. Third, this prediction is compared to the correct answer, that ground truth label we gave it during data annotation. And fourth, the model calculates exactly how wrong it was and adjusts its internal parameters, its weights and biases, to make a slightly better prediction the next time around. Now, this mistake calculation has an official name. It's called the loss function. In machine learning, the loss function tracks the degree of error in the model's outputs. If the model's predictions are accurate, the loss is small. If its predictions are wildly inaccurate, the loss is large. So the fundamental objective of all machine learning is to optimize the model to minimize this loss. We basically want that error calculation to get as close to 0 as humanly possible. Which leads us to Section 5, gradient descent explained simply. So you might be wondering, how exactly does the machine know which direction to adjust its parameters to minimize that loss? Well, it uses an optimization algorithm called gradient descent. I know, it sounds incredibly complex and intimidating, but the underlying concept is actually quite intuitive once you visualize it. Picture this. You are a blindfolded hiker, standing somewhere on a steep, uneven mountain. Your goal is to reach the absolute lowest possible point in the valley below. But because you're blindfolded, you can't see the valley. Instead, you use your feet to feel the slope of the ground right where you're standing. You figure out which direction points downward, and you take a small step in that direction. You just repeat this process, feeling the slope and taking a step over and over again. If the AI is our blindfolded hiker, gradient descent is this exact process of feeling the mathematical slope and taking small, repeated steps downward until reaching the bottom of the valley. And that bottom, that represents the lowest possible error or minimized loss. While the math behind taking a single downward step is relatively simple, the scale at which this happens today is just mind-blowing. Modern AI systems use massive data centers filled with specialized chips to recalculate this gradient billions of times across trillions of parameters. Just to put that into perspective, according to Epoch AI, the training compute power used for notable models has increased by an estimated 1.5 billion times from 2010 to 2024. 1.5 billion times. That is an unimaginable amount of raw computational power dedicated solely to taking those tiny mathematical steps down the mountain. And finally, Section 6, testing the AI model. So, after millions or billions of loops of training and adjusting, we're finally left with a finished model. But how do we know if the AI is actually smart, or if it just memorized the answers we gave it? To prove the model can truly generalize to the real world, engineers evaluate it using a strict separation of data. On one hand, we have the training data. This is what the model used to fit its parameters and step down the mountain. But on the other hand, we have the test data. This is a batch of information the AI has never been allowed to see before. It's held out specifically to provide a totally honest evaluation of the model's final performance on totally unseen, real-world examples. Because think about it. If the model performs amazingly on its training data but utterly fails on the test data, the model is suffering from a massive problem called overfitting. Overfitting is exactly like a student who memorizes a practice quiz word for word, gets a 100% on it, but then completely bombs the actual final exam because they didn't learn the underlying concepts. They just memorized the specific questions. We absolutely want our models to learn the patterns, not just memorize the data. So now that you understand the basic loop of how reality is transformed into data, converted into numerical learning, and optimized through gradient descent, consider the future for a second. We are generating more data than ever before, and computing power continues to absolutely explode. As we feed these massive digital brains even more of our reality, what completely unimaginable patterns, solutions, and insights will the next generation of AI uncover? It's a fascinating and maybe even a slightly intimidating frontier. Thanks for joining me on this explainer, and keep your eyes on the data. It really is the fuel for our future.